Welcome back, my rubber hearts. Today, we are diving into some of the most cutting edge rubber recycling technologies that are still in the research and development phase. These are methods that are being explored in labs, tested in pilot projects, and, if proven viable, could completely change the way we recycle rubber. Right now, rubber waste, especially from end of life tires, is a major environmental challenge. We can't just landfill this material indefinitely, and traditional recycling methods have their limitations. That is why scientists and engineers are working on new ways to break down rubber, recover valuable materials, and make the process more sustainable. We'll be looking at three of the most promising approaches: chemical recycling for isoprene production, which aims to convert waste rubber back into monomers; advanced devulcanization techniques, which seek to reverse the vulcanization process and restore rubber's original plasticity; and biotechnological methods, where microorganisms and enzymes are being explored as a way to break down rubber naturally. These technologies are still in development, but the progress being made is fascinating, and if they work on a commercial scale, they could revolutionize the industry. Let's get into it. One of the most exciting projects in this field, the chemical recycling for isoprene production, is being led by Bridgestone Corporation in collaboration with the National Institute of Advanced Industrial Science and Technology, the Tohoku University, ENEOS Corporation, and JGC Holdings Corporation. Their goal is to develop a chemical recycling process that can break down used tires into isoprene, which is one of the key monomers used in synthetic rubber production. This project is particularly significant because it aligns with Japan's Green Innovation Fund, which is focused on reducing industrial carbon footprints and promoting circular economy practices. The process itself relies on a specialized catalyst that enables the depolymerization of rubber at relatively low temperatures. Normally, breaking down rubber into its base monomers requires a tremendous amount of heat and energy, making the process inefficient and environmentally costly. But with the right catalytic system, the long polymer chains in rubber can be selectively broken apart, producing high-yield isoprene that can then be purified and used to manufacture new synthetic rubber. What makes this project so promising is that it's not just about recycling rubber. It's about creating a closed-loop system where all tires are converted back into their base chemicals and then turned into new tires again. If successful, this could drastically reduce the need for fossil fuel-derived raw materials in synthetic rubber production. It would also help tackle the issue of waste tires by giving them a high-value second life. While the technology is still in the development stage, the research partners are working towards commercializing it within the next decade. Advanced devulcanization techniques are a fascinating route because devulcanization has always been one of the holy grails of rubber recycling. Vulcanization, the process that makes rubber durable and elastic by introducing crosslinks, is what gives tire and industrial rubber parts their strength. But those same crosslinks also make rubber incredibly difficult to recycle. Traditional mechanical grinding can break rubber down into crumb rubber, but it doesn't restore its elasticity or allow it to be remolded into high-quality products. That is why devulcanization, the selective breaking of sulfur bonds while preserving the polymer backbone, is such an important area of research. There are several approaches being tested, each with its own unique working principle. One of the most promising is chemical devulcanization, which uses specialized reagents to target sulfur crosslinks. Studies have shown that organic disulfides, amines, and ionic liquids can act as selective cleavage agents, breaking sulfur bonds without damaging the underlying polymer chains. Research published in Nature Communications has demonstrated that dibenzyl disulfide can effectively weaken and break vulcanized rubber's crosslink network under controlled conditions, making it processable again. Another promising approach is microwave-assisted devulcanization, which works by using electromagnetic radiation to generate localized heat within the rubber matrix. Because sulfur bonds absorb microwave energy more efficiently than carbon-carbon bonds, they heat up and break apart first, leaving the polymer structure largely intact. This method has been successfully tested in pilot studies and could be scaled up for industrial use if energy efficiency concerns are addressed. Then there's the mechanical devulcanization, which applies high shear forces to disrupt sulfur linkages. A study conducted at the University of Twente in the Netherlands has shown that under extreme shear and pressure conditions, rubber molecules can be forced to separate at the crosslinks without excessive degradation. Combining mechanical devulcanization with ultrasound treatment has also been investigated, with some success in breaking down heavily cross-linked rubber networks. If any of these methods can be optimized for large-scale use, the impact would be massive. Instead of relying solely on virgin rubber, manufacturers could incorporate high-quality, devulcanized rubber into new products, reducing costs and environmental impact. Biotechnological approaches are one of the most exciting but still highly experimental approaches to rubber recycling. Scientists have discovered that certain bacteria and fungi produce enzymes capable of breaking sulfur crosslinks in rubber. This idea has been around for a while, but recent advancements in biotechnology and microbial engineering have made it a much more viable field of study. A fascinating study titled The Microbial Devulcanization of Waste Ground Tire Rubber Using A Ferrooxidants DSMZ 14882 and an unclassified sulfur oxidizing consortium explored how a combination of microbial cultures can be used to break down vulcanized rubber. Aciditiobacillus ferrooxidans, a well-known sulfur oxidizing bacterium, was used alongside an unclassified sulfur oxidizing microbial consortium to enhance the degradation process. The idea behind using both cultures is that different microbes contribute to breaking sulfur bonds in different ways. Some release enzymes that directly attack the crosslinks, while others create an acidic environment that weaken the rubber structure over time. The process works by submerging finely ground rubber in a bioreactor containing these microorganisms. Over time, the microbes produce sulfur metabolizing enzymes that gradually cleave the sulfur bonds. This method is incredibly slow compared to chemical or mechanical devulcanization, but it has the advantage of being low energy and environmentally friendly. Another notable research focuses on the bacterium Gordonia desulfuricans DSM 44462T. This microorganism has demonstrated potential in the biological devulcanization of ground natural rubber. In a study published in Applied Microbiology and Biotechnology, researchers evaluated the devulcanization ability of Gordonia desulfuricans through a designed set of experiments. The findings indicated that this bacterium could effectively break sulfur crosslinks in vulcanized rubber, offering a promising avenue for environmentally friendly rubber recycling. The mechanism involves the bacterium's ability to desulfurize compounds, thereby cleavaging the sulfur bonds that contribute to the rubber's vulcanized structure. This process results in the breakdown of the rubber matrix, rendering it more amenable to reprocessing. The study's experimental design aimed to optimize conditions for maximum devulcanization efficiency, highlighting the potential of G-desulfuricans in sustainable rubber waste management. If microbial devulcanization can be scaled up, it could offer a completely green solution for rubber recycling, without the need for harsh chemicals or extreme processing conditions. Right now, the biggest challenges are speed and efficiency. Biological processes take significantly longer than chemical ones, and optimizing microbial strains for faster rubber degradation is still a major area of research. These three technologies, chemical recycling for isoprene production, advanced devulcanization techniques, and biotechnological rubber breakdown, represent the future of sustainable rubber recycling. They are still in the research phase, but if any of them can be successfully commercialized, They have the potential to transform the way we handle rubber waste. Whether it's turning old tires back into synthetic monomers, selectively breaking sulfur bonds, or using microbes to naturally degrade rubber, these approaches could drastically reduce landfill waste, cut down reliance on virgin rubber, and contribute to a truly circular rubber economy. Thanks for turning into my rubber heart. If you found this episode interesting, don't forget to like, subscribe, and hit that bell icon so you never miss an episode. Let me know in the comments which of these technologies you think has the most potential, or if there are any other rubber science topics you'd like me to cover. Until next time, stay elastic and stay bouncy.